Good day. In this video, we are going to talk about optical fibers. We are going to define optical fibers, look at the physics behind this technology, and we will also explore its types. I am Jarideep Pidelicata. Optical fibers, by definition, are long, thin, transparent dielectric material which carries light from one end to the other end of the fiber by means of total internal reflection. So this is an optical fiber. And the picture in the right here is a global fiber optic network. And you can see here that it connects a lot of countries overseas. And what do these fibers connect? In turn, they transmit data at long distances and at great speed. So these are the basic parts of an optical fiber. We have the core. This is an inner cylindrical material made up of glass. The cladding. This is a cylindrical shell of glass or plastic that covers the core in a protective jacket or coating. This protects the fiber from the surrounding. One important thing to note here is that the refractive index of the core is slightly higher than that of the cladding. This is very crucial for total internal reflection, the means to propagate light in the fiber, to be understood. Total internal reflection happens as light from a denser medium, that is the medium with the greater index of refraction, light from that medium is totally reflected back to the medium as it hits the interface between a less dense medium. To understand this, let's visit the law of refraction. This states that the ratio of the sine of the angle of incidence to the sine of the angle of refraction is a constant. Here we have n sub 1. This is the index of refraction from the denser medium. Sine theta 1 is equal to n2 sine theta 2. Here we substitute theta 2 to be 90 degrees because this is the angle of refraction when we have the angle of incidence to be the critical angle. So we have n1 sine theta 1 equal n2 sine of 90. Sine 90 is equal to 1. And we have n1 sine theta 1 is equal to n2. And here, theta 1 is just equal to our critical angle. That is equal to inverse of sine times n2 divided by n1. And whenever the angle of incidence from the denser medium exceeds this critical angle, total internal reflection will happen. So this is the core cladding interface. We have an incident light ray. It hits the fiber axis here, refracted, and the angle of refraction is greater than the critical angle, and so we have a total internal reflection here. So the light ray is back to the medium. Let's talk about the maximum acceptance angle. So the maximum acceptance angle is the maximum angle of incidence at the end face of the optical fiber of which the light ray can be propagated along the core cladding interface. Looking at this core cladding interface, looking at this figure, we have, by the law of refraction, n0 sine theta sub I is equal to n1 sine theta sub r, or the angle of refraction. And this will be our equation 1. From the right angle triangle ABC here, we have theta r is just equal to 90 degrees. So this is 90 degrees minus theta. And so we can substitute theta r to be 90 degrees minus theta. And this term is just the same when you get the cosine of theta. And we have the equation 2. You have sine theta sub I is equal to n1 divided by n0 cosine theta. When theta is a critical angle, theta sub c, the angle of incidence is the maximum angle of acceptance. We have sine of the maximum angle is equal to n1 over n0 cosine of theta sub c, and this will be our equation 3. According to the law of refractions, we have n sub 1 sine of I is equal to n2 sine of r. So we have I to be theta sub c, and then we can use here r equal to 90 degrees. So that's our condition. So we have sine of theta sub c is equal to n2 over n1 sine of 90, but sine of 90 is equal to 1. And we have here the sine of our critical angle is equal to n2 over n1. So we use a trigonometric identity here, and we come up with cosine of theta sub c is equal to the square root of 1 minus sine squared theta c. We have a value for sine theta c, and we just substitute that here, and we can have the equation 4. And so we substitute equation 4 in 3, and so we have this equation. And so we can cancel n1s here, and we are left with n0 in the denominator. But if the medium surrounding the fiber is air, n0 is just 1, and so we can, and that is why we don't see that in here. So you have sine of the maximum angle is just equal to square root of n1 squared minus n2 squared. And so the maximum angle is just equal to sine to the minus 1 square root of n1 squared minus n2 squared. And so this is now the equation for the maximum angle of acceptance. And this is very important. It's because if you exceed the maximum angle of acceptance, you will not be able to observe total internal reflection. So rotating the acceptance angle about the fiber axis describes the acceptance cone of the fiber. Light launched at the fiber end within this acceptance cone will be accepted and propagated to the other end of the fiber by total internal reflection. Now let's talk about the numerical aperture. This is the light gathering capacity of the optical fiber, and this is equal to n0 sine of theta max. And then the sine of the maximum angle is equal to square root of n1 squared minus n2 divided by n0. And here we assume that n0 is just equal to 1, and so we can equation here. This is a difference in two squares, and so we can express it into these terms. Let us also consider fractional change, and this is now the ratio between the difference in refractive index of the core and the cladding divided by the refractive index of the core. And so we can extract this term here and just simply put delta. Here n1 is approximately n2, which is usually the case because the difference in the refractive index of the core and the cladding is just very small. And so we assume that they are almost equal. And so we can change this into 2n1, and if we multiply that with another n1, so we have here 2n1 squared, and then we have, of course, the change. We can take that out of the square root, and so we have n1 squared of 2 delta. So this is our numerical aperture, and this is the light gathering capacity of the optical fiber. Now let's go to the types of optical fiber. This is based on duration of refractive index of the core, because based on mode of propagation, the fibers are further divided into single mode and multi-mode. So we have step index fiber and the grade. Oh, this is just graded index fiber. For the step index fiber, we have single mode and multi-mode. In the single mode, the refractive index is constant in the core. The core diameter is about 8 to 10 micrometer, and the outer diameter of the cladding is 60 to 70 micrometer, and there is only one path for light ray propagation. This is extensively used because distortion and transmission losses are very less. For multimode step index, the core and cladding dimension are much larger to have more number of paths. So this is one of its main difference. The core diameter varies from 50 to 200 micrometer, which is relatively large compared to that of the single mode fiber. And the cladding diameter also is 100 to 250 micrometer. And this two types of step index fiber are reflective fiber since light is propagated in the form of multiple total internal reflections. Let's go to graded index fiber. Radially, the refractive index of the core decreases from the center to the surface. This causes light rays to have continuous refraction. The propagation of light here is due to refraction, and therefore, this is a refractive fiber. Near the surface, light ray travels faster and catch up with the distance traveled by rays along the axis. Therefore, all rays arrive at the same time at the end of the fiber. This fiber can be single mode or multi-mode. The diameter of core and cladding varies from 50 to 200 micrometer and 100 to 250 micrometer, respectively. So this is the cross-section, refractive index profile, and light path of the types of optical fibers. So you have a multi-mode graded index. We have the multi-mode step index and the single mode here. You notice here that it has a very small core. And here, this is the light path of a multi-mode graded index. We can also see here that the refractive index decreases from the center to the surface, whereas here in the step index, it is just constant. Now let's talk about optical fiber in communication system. This is one of its main applications. It essentially consists of the following parts. You have the encoder. The encoder converts signal to binary data. Binary data are transmitted as electrical pulses. And this electrical pulses is provided by the transmitter to the light source. Whenever the binary digit is 1, there is an electrical pulse, otherwise there is none. Then a fiber communication system also has a waveguide. This is a structure that guides the waves, core, the cladding, and the whole structure that guides the wave. The receiver then receives the pulses of light and turns them into electrical pulses. These electrical pulses have equivalent binary data, and the decoder can decode them into the information that is being transmitted. And so here is a block diagram of the optical fiber communication. So you have the encoder, the transmitter, the light source with an on and off mode of transmission. So the light will then travel here, no, something like that. It has to have a total internal reflection. So it's not perfect, but something like that. And they could be in different time intervals, different length, and that would give us a different kind of data. And that would give us the unique information that is being sent. Attenuation or power loss in optical fiber. So the power of light at the output is found to be always less than the power loss in the input. Attenuation is found to be a function of fiber material, wavelength of light, and length of the fiber. This is measured in decibels. Attenuation are mainly of three types. You have the scattering loss, absorption loss, and bending loss. And that's it, guys, for this video. Thank you so much for listening. I hope that you learned something. May God bless us all.